So hello everyone, my name is Giora. I'm a PhD student at Tel Aviv University. I'll be speaking about my work with Saron Rosset about using random effects in deep learning to account for correlated data, specifically focusing on high cardinality categorical features and repeated measures. Okay, so as a motivational example, let us look at the UK Biobank's electronic medical records dataset. The UK Biobank is a cohort of 500,000 volunteers who are being followed since about 2010. Here I want to focus on a subset of about 50,000 patients with cancer history who were tested for various blood chemicals such as cholesterol, calcium, protein, etc. Suppose we want to save those patients the blood test. We probably couldn't do that, but we could at least direct doctors to unusual measurements by predicting those blood chemicals results. So this is our table with 50,000 rows and our predicted measurement, say cholesterol level. I want to say statisticians have long recognized that often the data we see are correlated and that statistical models are better in various aspects by accounting for this correlation. This could be correlation due to very high cardinality, categorical, or cluster features like cancer type, which can take thousands of values. These categorical features have such a large dimension that machine learning practitioners sometimes prefer to ignore them. Or spatial correlation, like coordinates columns, stating from where our patients come across the UK, or even temporal correlation, because the blood test was not administered at the same day, or we have repeated measurements per patient. This phenomenon, by the way, isn't exclusive to tabular data. We often see, for example, computer vision applications trying to predict a facial feature, completely ignoring the fact that many facial images that the model was trained on come from the same individual. Here I want to focus on high cardinality categorical features, and in this specific data set, we have a few. Cancer type, tumor histology, previous operation, previous diagnosis, previous treatment. All these categorical features can take thousands of values, even tens of thousands. What do we usually do with these? Current solutions to deal with categorical features are one-hot encoding and entity embeddings. One-hot encoding is when we add Q additional binary features for the Q levels, and you can see how it quickly fails to scale and is prone to overfitting. Embeddings is when we lower the Q dimension to a low dimension D with some dictionary of size Q over D that is learned during training. For specific tasks and different features, this dictionary cannot be transferred and needs to be relearned. Plus, there is the need to store this large dictionary. Then there is the option to simply ignore such features. It's not that uncommon. The TLDR version of what I'm about to show is that treating these high cardinality categorical features as random effects seems to work very well. Our approach, which we call Lmmn, with a simple neural network, can reach the best mean squared error when predicting various blood chemicals measurements, as opposed to one-hot encoding or entity embeddings, which tend to severely overfit the training data. We'll see some more examples later. Okay, so for me to talk about random effects, I need to do a very quick overview of linear mixed models. Here we have n measurements in Y, and we model them as the sum of a fixed and random parts. The fixed part is what we know from linear regression, and beta is a vector of fixed parameters to estimate. The random part is similar, but now B is a vector of random variables, meaning that they have a distribution. Usually we assume a Gaussian distribution with mean 0 and some correlation structure D, and a lot depends on the structure. Finally, we have the usual Gaussian noise term with mean 0 and sigma squared E. Here we're focusing first on the random intercept model for single categorical features of Q levels. So D is diagonal with a variance term sigma squared B on its diagonal. Z is binary matrix, and if I write the model in scalar form, like here, you can see that for each cluster J, apart from the common intercept term beta 0, there is an added random intercept term B little j. So what do we expect to gain from the random effects approach in deep neural networks? We hope for a better model, which would take under consideration the correlation in our data. We hope to be able to handle categorical features of much higher Q, certainly not ignore them. Ultimately, this should lead to better performance, and bonus, we are also able to scale what statisticians know as nonlinear mixed effect model. Okay, so in our approach, Lmmn, the fixed part is now the output of a neural network. And as we shall see, this could be almost any neural network. The random part is also a result of some neural network, could be a different one, or embeddings, multiplied by the same vector of random effects B. Often we simply choose G to be the identity function and Gaussian noise as before. And again, we first focus on random intercept because of some very nice properties. I'll talk about our extensions in a few minutes. Here you can see a schematic description of Lmmn with a simple network. F and G enter a combined NLL loss, which I'll discuss in a bit. As you can see, this is a single stage training. So how do we do this? We write the marginal distribution of Y. It is Gaussian with covariance matrix V. And this is our loss function, which we minimize, the negative log likelihood. Here Xi is a stochastic batch of size M. So at each iteration, we're computing a smaller version of the loss. We use existing deep neural networks machinery, which is stochastic gradient descent and auto differentiation. And after training, we predict the random effects B and Y test. I wrote here that for the simple case of random intercept, we can avoid the inversion of V, which can be very large. It is N over N. Another approach we use is sampling. Okay, so we have many simulated results in our paper, but here I'm going to dive only into some more real data results. So first, a single categorical feature. You can see here for some real data sets with Q, that's the number of levels in our categorical features, ranging from a few hundred levels to about 40,000 levels. We use a varied types of data and network architectures like LSTM and convolutional neural networks, and our approach manages to decrease the test mean square error significantly. This is the UK Biobank table we've seen earlier with multiple high cardinality categorical features. Specifically here, there are 5. This is a more recent application with a more complicated correlation structure, where we use 50,000 Airbnb listings in New York City to predict the log price. We have one categorical feature of host with 40,000 different hosts and one spatial feature of location with 12,000 different listing locations. And our approach, which takes under consideration correlation within the hosts and between locations, performs best compared to embeddings and ignoring. Notice that here the level of dimensionality, one-hot encoding is completely impractical. So why does it even work? It's actually a really interesting theoretical problem. The main challenge in proving that the stochastic gradient converges to the full gradient in any way is the fact that it computes the inverse and log determinants of the V matrix in small parts on mini batches. Yet for the simple random intercept model, we can show that this is in fact valid if every batch consists of the nj observation of the categorical features level j. Okay, these are some extensions I don't have time to talk about. And this is a link to our code. We currently work with Keras. The key feature of our implementation is a custom Keras loss layer called NNL, which I show here. You can plug into a standard Keras MLP for tabular data with very little added effort. And that's it. I hope you will use Lmmn and see you guys in the future for our extended work. Thank you.